Okay, so here we're going to have a look at higher order polynomials. In the advanced maths course, you don't need to do much with higher order polynomials. You might need to graph them. If you're going to graph them, we're going to cover one method of graphing here, but there will be other methods of graphing which are encouraged and taught later on. So let's talk about what a polynomial is. So a polynomial, meaning something along the lines of poly, many, nomial number. It's a many-numbered term where the terms are added or subtracted from one another. We will be dealing with polynomial terms of a single variable. So the polynomials we'll be looking at all take the form y equals a times x to the n plus b times x to the n minus 1 plus c times x to the n minus 2 plus and so on, all the way down to some number term, which we'll call z. This is an nth order polynomial. Nth order polynomial. The order of a polynomial is whatever the highest power is. So in this case, x to the n, then there's x to the n minus 1, n to the n minus 1 is less than n, so the highest power is n, so this is an nth order. So we can have a zero order polynomial is of the form y equals, now notice, in this polynomial, x to the n minus 1, n minus 2, this will go down all the way till x has a 0 power. So this will be something of the form ax to the 0, but we know x to the 0 is 1, so this is just a. This is y equals a. This is essentially a constant function. So an example of a zero order would be y equals 3. There's not really anything you can do with zero orders. They are typically solutions in of themselves. Y equals 3 is a solution, not necessarily a formula that you can solve. We then have first orders. So first order means the highest power is 1 as opposed to a 0. So this is y equals ax to the 1 plus bx to the 0. X to the 0 is a 1. So this is ax plus b. Now you'll notice this looks very similar to y equals mx plus b, which is the linear equation you've seen, and that's because it is. The linear equation is in fact a first order polynomial. So this is just a line where the a and the m are the slope, and the b are the y-intercept. We then have a second order polynomial. This is y equals a x squared plus b x to the 1 plus c x to the 0. So this is actually ax squared plus bx plus c. Now this is a monic, non-monic, quadratic. So this is what you should recognize as a quadratic. And these you've already dealt with. These you can graph by finding the roots, you can shift it, you can refactor it, you can do a whole bunch of things. So these are the three most common types of polynomials that you'll see. But in this course, you will also see some third orders. So you might see some third order polynomials. These are polynomials of the form y equals ax cubed plus b x squared plus cx plus d. Now, third order polynomials typically they have a few different shapes, but they generally either look like this. This is a positive x cubed polynomial, or this. These are both third orders. If they're negative x cubed, they'll either go down like this, or they'll go down like this. So these are the general shapes of these third order polynomials. When you're asked to graph them, the first thing you have to do is you have to recognize, well, is this a positive one or a negative one? Because if it's a positive one, you know that it is one of these two, roughly speaking. If it's a negative, you know it's one of these two. We're going to rely on a very specific variation of mathematic formula in order to graph these third order polynomials. And this is the fact that the third order polynomial formula listed up here has a different variation. It can, for many third orders, can be written in a different way. So we can write a lot of third orders in the form y equals alpha times x minus beta times x minus theta times x minus phi. And this is such that beta, theta, and phi are the roots. So immediately, if you can recognize something is a cubic, this is third order is also known as cubics. So common name for this is cubic. If you can recognize something as a third order or a cubic, and you can get it into this roots form, these are the three roots of the third order. So if you draw them in a grid, maybe one's here, and one's here, if you know this is a positive cubic, it's got to go up this way, got to go down this way, it must do this. So if you identify something as a third order, you know that it's either a positive third order or negative third order. You sort of know what its shape looks like. If you can then find a way to get it into this roots form, we sometimes refer to these as roots forms, then you can identify what the roots are, graph them on the plane, and draw the positive or negative cubic through them. So I'll give you an example. I'll do one example, and then I'll let you have a go at a different example. So the example that I'm going to use here is going to be to graph y equals, let's say, x plus 3 times x plus 1 times x plus 6. Now, we know this is a cubic. We could expand all of these out, and if we did, it would have an x cubed term at the beginning, because we get an x times an x times an x, and it would be positive. So immediately we know it either looks like this or like this. It's one of these two shapes. The roots form tells us that these three values, the beta, the theta, and the phi, are the roots. So we need to change the sign of these. So minus 3 is one root, minus 1 is another, minus 6 is another. So let's draw a graph, and let's graph our roots. Minus 1 here, minus 2, minus 3 here, minus 4, 5, minus 6 over here. We know it's a positive cubic, so we know it's got to go up this way. We know it's got to go down this way. Must curve through here, and then must curve through here. So this is an approximate graph of a third order polynomial or cubic. Now, a lot of the graphing that you'll do in the year 11 part of the course for cubics is not going to be hugely accurate. So this is typically considered to be enough for the types of graphs. If your teacher wants you to be more accurate, you can plug in the midway point of these 2 points to find this point. You can plug in the midway point of these two to find this point. You can find the y-intercept by letting x equal 0. You can find other points if you want to make it slightly more accurate, but usually finding the roots and the general shape is sufficient. Later on, you'll use other tools to make these graphs better, including derivatives, but for now, finding roots is a very suitable way to approximately graph cubics. All right, so I'm going to let you have a go at an example. So the question that I'll give you here will be y equals 6x squared minus 2x cubed. Now notice this is not in factorized form. So you have to factorize it first, try and get it in a roots form, and then try and graph it. So pause the video now and have a go. Good luck. Okay, so now that you've done this, let's go through this. We know it's a cubic. It's got an x squared and x cubed. It's third order polynomial. The cube term is negative, so it's either this one or this one. It has one of these two general shapes. It's not in the roots form, but we can get it into the roots form by factorizing. So we can do a simple factorization here. We can take 2x squared out of both of these terms. So we get 2x squared in front of 6x squared divided by 2x squared is 3. 2x cubed divided by 2x squared is minus x. And so now what we've actually got is 2 times x minus 0 times x minus 0 times x minus 3, and then this negative comes out the front here. So this is a roots form. 2 of this cubic's roots are at 0. So x equals 0 is one double root, and x equals 3 is going to be another root. So let's draw this. And by knowing the roots, whether there's double roots or single roots, we'll be able to work out what the thing is going to do, because we know its general shape is negative. So x is 3, 1, 2, 3, it's over here. X is 0, that's here. It's a negative cubic, so it must come down like this, and it must go down over here. Well, the only way to fit a cubic curve in here is for the cubic to turn up here and then back down. And that's in fact what it does. If you have two of the values in the cubic root formula giving you the same value, that's what's known as a double root. So this here is a double root. And what happens at a double root is usually the curve just touches the axis and then turns around. And this is the graph of our third order polynomial, or our cubic function, and this is how you approximately graph these cubics. Don't worry too much about the exact curvature of them. You'll be able to improve them later on when you have access to derivatives. But for now, this is a pretty good graph.